Okay, as I said here in the previous, you can see the heat and the coefficients of all these chemicals. If you have heavy hydrocarbons, light hydrocarbons, flue gases, steam, so these are all the coefficients, right? And the resistance is 1 by U is the resistant. So you get the resistance of your shell side, you get the resistance on your tube side. So this I think you have already know in your college. The total U is the resistance of the shell side, tube side, then resistance on the wall. Then I'm going to give the fouling resistance. This you will get it. So you need to add the fouling resistance on the tube side, fouling resistance on the shell side, then the wall resistance. What type of material that depends on the thickness of the wall and the material of the wall. Okay. So based on that, you have to find it out, the wall resistance. So these are all the resistance, right? All the resistance, and one, if you inverse this resistance, is your U. So 1 by 0.002515 is nothing but 397. So you can take roughly around 400, and you can size it. In this example, I want to take it as a counter current. So counter current, immediately what I'll do, the inlet is 100, outlet is 75, hot fluid. The cold fluid, counter current, right? Counter current means opposite direction. No, it's not co-current, counter current. So inlet is 40, outlet is, so you do this and you get the subtraction, 30, 35. Then simple. What you do? 30 minus 35 divided by ln 30 minus 35, right? So once you know the graph, once you put it, it is very simple. You don't need to remember the formulas, just do it. So when you do it, you get the LMTD. Then again, once you do the LMTD, use the graph. These graphs are available, and based on the graph, try to find out the correction factor. Okay, one more thing I want to tell you. If this correction factor is more than 0.85, that means you have selected a wrong type of shell. Simple. Okay. So remember, it should be less than 0.85. Ideal to be around 0.9 is very ideal. Anything, see the correction factor, if it is more and more, that means your selection of your shell is correct. The selection of your the type of your exchanger that you have selected is correct. So whenever you have this correction factor, if it is coming more than 0.85, I can 100% I can tell you, you have selected a wrong type of shell and tube exchanger. You need to modify it. You need to have a different type of exchangers. Okay. So this graph, this graph is only for one shell and two pass. So this is, so you need to know, this is like this. You have several graphs: 2 shell, 4 pass, 3 shell, 6 pass. So you have different configuration, and all these graphs you have to see. You have these graphs. That is why the tool come very handy. When you have these tools, the tools inbuilt all these graphs, everything, and it will do it for you. Manually, you have to do it means you have to do it using Gautier Perry or Kern. Yes, Kern, one of the best book for heat exchangers. There is no absolute book other than Kern for heat exchangers. DQ Kern. Now, once you know the correction factors, see in this example, the LMTD is around 32.4, right? But when you add the correction factor, the actual LMTD, the MTD, the mean temperature difference becomes 30. So it is not 32, right? So this is where this is important. So based on this, your U. So you know the UA LMTD, UA MTD. So in that MTD, you substitute, you have assumed the U and you calculated the area. So this is how you do it. This is how you size your heat exchanger. Okay, the area is fine. Once you know the area, then tube side, shell side, everything we need to do it. Now another important thing, very important thing, people make mistake, shell nozzle sizing. Remember, nozzle sizing for a gas, for a liquid, you need to have rho V squared 5000 to 6000. Rho V squared 5000 to 6000. This is standard. For the gas, it can be 2200 to 2500 it can be. So again, I want to do this example, but the time is limited. We have to see a lot of questions. There will be some discussion also. So I'm going to go fast. So you assume the rho v squared, since it is a liquid, you assume to be around 5,000, maximum 6,000. Don't go more than that. Then based on that, you get the velocity, because our velocity should be less than 2.5. More the velocity means you have more entrance loss. More the entrance loss is not acceptable. So entrance loss, that is why this is very critical to have the velocity around 2.5 in the nozzles. Okay, so once you know the rho v squared, so you assume this 5,000 is very ideal. So when you assume it, you get a value, the velocity value, it is less than 2.5. It's good. The nozzle area. So nozzle area, now you know the velocity, you can back calculate the nozzle area. So nozzle area, what I back calculated, the mass flow in seconds, then density, velocity. So once based on that, I'll calculate my nozzle area. Once I know my nozzle area, the nozzle ID can be back calculated. So what I got is 5.4 inch. There is no 5.4 inch. The next size is 6 inch. So I have to go for a 6 inch nozzle. This same thing up if it is a gas, you have to do it based on that. Again, HTRA doesn't do it. You have to give the rho v squared values. Okay, you have to, the HTRA give you the rho v squared values. You have to verify it. You have to see the rho v squared for the liquid is, this is not only for exchangers, even separators, the rho v squared values you have to see. Okay, any nozzles, the rho v squared for the liquid and gases. Now, this is little bit theory, but I want you to understand the concept behind it. We don't see, generally once you pass out from the college, it is very difficult to remember all these equations, but it is always good to remember the concept behind these equations. Fundamental equation we are going to deal, state-of-state equation or a Ditter-Boltus equation, fundamental of your heat transfer, right? So what I want to tell you, it's the equation, the state-of-state or a Ditter-Boltus equation. What it deals with the Nusselt number, it is a relationship between the Nusselt number, Reynolds number, Prandtl number. So the important thing I want you to remember is heat transfer coefficient is directly proportional to the mass velocity. Remember, mass velocity directly proportional. If you increase the mass velocity, heat transfer coefficient will increase. If you increase your specific heat, your heat transfer coefficient will increase. If you increase your thermal conductivity, your heat transfer coefficient will increase. Remember this. You should not forget that. If you increase your viscosity, heat transfer coefficient, there will be some small amount of reduction will be there. So this is the concept I want you to remember. Okay. Equations, always good for your exams. Concept for your life. So remember the mass flow velocity, the viscosity, thermal conductivity, specific heat. Now, when you deal with gas, the heat transfer coefficient of a gas is very low. Why heat transfer coefficient of gas is very low? I don't know, I think since there is a time constraint, I'm going to answer myself. But just think about it for a second. Why the heat transfer coefficient of gas is very low? Any idea? I don't want to confuse this. Simple. Heat transfer coefficient is directly proportional to your thermal conductivity. So thermal conductivity for the gas is low. That means heat transfer coefficient is low. 1. Remember. Number 2, density. Gas has low density. So for a specified pressure drop, with the low density, you will have your mass velocity will be low. So remember, for a specified pressure drop, the low density means low mass velocity. So low mass velocity, you will have low heat transfer coefficient. So this is how the concept, you should know the concept once you remember why these are related, right? So that is why, but at the same time, when you increase the gas pressure, what will happen if you increase the gas pressure? The heat transfer coefficient will increase because you are going to increase your mass velocity, right? So this is what you should understand from the concept. So this is again a tube side heat transfer coefficient. We have a lot of empirical graphs are available, Reynolds number, how it is been related. Then you can find out and you can get the heater, the coefficient. I don't want to discuss much because of the time constraint. Another important thing I want to discuss is your pressure drop. Remember, pressure drop is directly proportional to your mass velocity. Pressure drop is directly proportional to your length, right? More the length, more the pressure drop. Inversely proportional to your density. Pressure drop inversely proportional to your density. That is why gas will have less pressure drop, liquid has more pressure drop. So I hope you to remember this fundamental concept. So when you design a heat exchanger, you are going to play with all these things. Velocity. Okay, why the velocity? Okay, the length, right? And if you have the density, so all these things, you need to know, and this is how you need to optimize it. Clear? So again, as I said, what are the things that you should consider? The tube pitch, tube layout pattern, spacing and cut, shell style. What is the shell style? As I said, the TEMA classifications. So remember all these things, whatever I said, where to use E shell, where to use J shell, where to use A, where to use B, where to use W, where to use S, where to use T. So whatever I said, make a note of it. Okay, eventually when you go to the industries, you see all these things. You can, now I'm going, and what I'm given is dots. I've given you a lot of dots. Now, I request you to kindly go and join all these dots. For joining these dots, I humbly request every engineer to go to industry and see it. Once you connect all these dots, you will get a wonderful picture and you will start loving your subject, your heat exchangers. This is an ocean. Whatever I've given you is a drop of an ocean. Just giving you some small hints. This is not everything. This is just a hint. So I want you to kindly go through it. And when you go to the industries, when you go to your labs, heat exchanger lab, you may have your, I believe you may have your industrial heat exchanger. Go through it, see it, feel it, calculate yourself. You calculate yourself. You connect these dots, whatever I said, the dots, then you will get a beautiful picture. Okay. So I have few slides also, which I don't want to confuse you, but in time permits, you can send me an email. I can send you a lot of information on heat exchanger sizing, the rule of thumbs, everything. But other than that, because of the time, I want to have at least little bit time for more question and answer session today. Let's see. Over to